Hey guys, good morning. Hope you're doing well. It's a little blustery out today, so probably hanging out inside, just dying to watch some notes about simple machines. So I'm glad you're here with us. What we're going to do today, it should be pretty quick. We've already covered sort of the basics of simple machines, sort of what a machine is, how they can be helpful, how we calculate mechanical advantage. And so we're going to be looking at a few more examples of simple machines today. Okay. So the last time we studied inclined planes, and we learned a little bit about them. Today we're going to actually learn about two simple machines that are really nothing more than inclined planes used in a slightly different way. So the first simple machine for us to talk about today is the wedge. And the wedge is basically it's a double-sided inclined plane. Okay. So what does that mean? If we look at this diagram here, okay, I got a new tool. If we look at this diagram here, what we see is that we have an inclined plane. Here's one inclined plane. Okay, and then we can look at right next to it is another inclined plane stacked together. And this double-sided inclined plane can be used because you use this wedge by applying this downward force, okay, on this part of the wedge. And that force is then multiplied, and it's also exerted outward. So this downward force that is being applied exerts a force outward, which can then split or cut a material. Okay, so it transfers this downward force into an outward force, splitting things. Okay, so the longer and the thinner the blade, the greater the mechanical advantage of this wedge. Which makes sense because if you imagine it as an inclined plane, the longer this inclined plane is, the greater mechanical advantage it's going to give. Okay, and so some examples of a wedge in use, a log splitter. So I'm not sure if many of you have used this, but this log splitter is basically just a metal wedge. Okay, and you put this metal wedge on a log like this, a round sort of big log, and then you hit it with a sledgehammer or some heavy hammer, and as you hit that, the downward force of the sledgehammer is transferred to outward force, pushing out, which then splits the log in half. I mean, this is a manual log splitter. They also have machines which basically take the place of the sledgehammer and use a piston to apply the force, but the wedge itself works in the same way. Basically, anytime you have a cutting instrument, that's a wedge. A knife, a nail, scissors. Okay, those are wedges that can separate objects by changing the direction of the force. And here you have just an example of that. The blade of the knife, you're putting the force in a downward motion. Okay, and that force is transferred outward, splitting this slice of cake in two. So that's a wedge, basically an inclined plane turned on its side. Another simple machine for us to talk about today is a screw. Okay, so we're all familiar probably with a screw, and if you imagine what makes a screw, how is it different from a nail? Well, there are the threads. That's what makes a screw different from a nail. Okay? And you could think of the threads of a screw as basically an inclined plane that's wrapped around a cylinder. That's what the threads are. So screws are often used for fastening objects together, for bringing objects closer together. Okay, so if you imagine a screw as we see here, these screws, you can use them to join, let's say, two pieces of wood together. So let's think about let's say you could join two pieces of wood together either using a nail or using a screw. So think about which would require more force. Obviously the hammer. So for you to hammer a nail and to hold two boards together, you have to hit it with quite a bit of force, with a heavy hammer. Okay. If you imagine a screw being used to join two pieces of wood together, you can use relatively little force. You can use a single hand just to turn that screw little by little, which will bring the screw into the wood, joining those two pieces together. And it allows you to use less force. But again, we have to always think about this. What's the trade-off? So if I'm using less force to get the screw into the wood, what's the trade-off? Well, it's always distance. I have to turn that screw several times, many times, to move it into the wood, even just a little bit. Okay. If you were able to take the threads of a screw and kind of unravel them, that's what we're looking at down here. What you would see, it's just an inclined plane that's been wrapped around a cylinder. Okay. Examples, obviously a screw is an example of a screw, but the lid of a jar has threads on the inside, and that's a screw. That as you turn the jar lid, okay, it brings the lid closer to the glass that you're joining it to. A drill bit. This is a jack used to lift a car up off the ground. And this works a little differently because this is a very long screw here. And as you turn this screw, it slowly brings these two parts together, lifting up a car. So basically, you can use a screw to lift a car off the ground using just one hand. If you ever have seen one of these jacks, you could just use one hand, crank it, and lift a whole car off the ground using very little force from your hand. Now, again, you think about the trade-off. There's always the trade-off. That, yeah, you can lift a car off the ground with one hand, but you have to turn the handle of this jack hundreds of times just to lift the car a small amount. There's always this trade-off, distance versus force. I can use less force, but I'm going to have to do it for a much greater distance. The same is true of these screws. Okay. The steeper the threads of the screw, the lower the mechanical advantage. So it's a little difficult to see in this diagram, but if we have, let me go to the next slide. So it's clear. So I have two screws here, screw A and screw B. Okay, they're both screws, both have an inclined plane. If we look at these, just looking at them without looking at the details, which would you say has a higher mechanical advantage, a greater mechanical advantage? If you said A, correct. A has a greater mechanical advantage. Okay, it has threads which are closer together. There's more threads, and they're not as steep. If we look at screw B, there's fewer threads, they're steeper, okay, and they're spaced out farther apart. Okay. If you imagine, if you're going to use screw A and you're going to screw it into a piece of wood, okay, you're going to have to turn the screw many times to get it into the wood. Screw B, you would have to turn it fewer times to get it into the wood. But think about what the trade-off is. You would have to use a lot greater force to turn screw B than you would screw A. So there's the trade-off. You can measure the mechanical advantage of a screw. One way to do this, if you actually have the screw in front of you, is you can take a piece of string and you can wrap it around each thread of the screw till you get to the end. Then keep your fingers where these string ended. Unravel it, and what you'll see is the length of that string is the length of the screw threads. Okay, and you can measure that. And if you're to do that, what you're actually measuring is the length of the threads, which is the effort distance. So again, we can calculate mechanical advantage of a screw. So if I were to do that with screw A, and I wrapped the string around each thread, stretched it out, measured it. Let's say I came up with a measurement of 16 centimeters. And the resistance distance is how long the screw actually is. In this case, it would be this long, 2 centimeters. So what would the mechanical advantage of the screw be? Obviously, it would be 8. If I were to do the same with this screw, screw B has fewer threads. I'd wrap that string around, stretch it out. If I found it were 8 centimeters long, the screw itself is the same length, 2 centimeters. This screw B would have a mechanical advantage of 4. So what does this mean in reality? Well, screw A, which has twice the mechanical advantage, I would have to use half as much force to turn that screw. But I would have to do it twice as many times to get it into the wood. So that's how a screw is used, and that's how we calculate mechanical advantage. The final type of simple machine for us to talk about today is called the wheel and axle. Okay. A wheel and axle is made up of a larger, what we call wheel, which is attached to a smaller rod called the axle. When you turn the wheel, the axle turns with it. And so a wheel and axle can be used to multiply your force. So here I have a picture of a doorknob. It's not in a door, but a doorknob is an example of a wheel and axle. The outer part of the doorknob that you grab onto is the wheel. The smaller central portion is the axle. So, in our house, we have an old house, and sometimes the doorknob actually comes off, okay, and just the rod is sticking out. I have to get my screwdriver and put it back on. But I don't know if you ever have seen that situation, okay? If you were to try to grab the rod that's sticking out and try and turn it, it's really, really hard to turn. You can move it a little bit, but it's really hard. You have to have that larger knob attached to it, because what that knob is doing is it's multiplying your force. And the larger the knob, the greater the multiplication of your force. So in this example, okay, the radius, we use the radius of each portion to calculate mechanical advantage. So in this case, the radius of the knob part is 12 centimeters. The radius of the axle part, so the wheel part is 12 centimeters. The axle is 2 centimeters. That's the effort distance, is the radius of the knob. Resistance distance is the radius of the axle. And divide those, the mechanical advantage of this doorknob is 6. So the force that I use to turn the knob is multiplied 6 times to turn that axle. The wider the knob, the greater the mechanical advantage. But again, there's the trade-off. To turn that axle just a small amount, I have to turn the larger knob a greater distance. Some other examples of wheel and axle. A wrench. Okay, so a wrench has a small portion that fits over a bolt, and then it has a long handle. You could imagine that the handle of this wrench is actually part of wheel and axle. If I imagine this, okay, if I were to extend this, okay, around, oops, sorry, my drawing on the mouse pad is not good. Okay, that's the wheel. And this small section here would be the axle. And so I move this end of the wrench, okay, and it turns this bolt. But there's the trade-off. I have to move this a far distance just to move this bolt a short distance. Okay, but my force is being multiplied. And the longer this wrench is, the greater mechanical advantage. Okay, so if you ever have a bolt you're trying to loosen, do you ever know that loosen and unloosen mean the same thing? Kind of weird, right? But if you are having trouble, if you get a longer wrench, that's going to multiply your force even more and therefore give you a greater mechanical advantage. So if you can't get it loose with a shorter wrench, try a longer wrench. Another example, the faucet handle. Okay, this is a wheel. Okay, so here's the wheel and here's the axle. So even though it's not actually shaped like a circle, like a wheel, it really is a wheel and axle. And so by turning that knob, using this portion here, okay, you're exerting a greater force on the axle, and you can unscrew that with relative ease. A well in a bucket or a boat lift, they work using a wheel and axle. You know, I don't know if you've ever seen one of these. Sometimes you might see them at a lake. People put their boat on this, or maybe a jet ski. And so if you ever used one, you may notice you pull the boat or jet ski onto this platform, which is lowered in the water, and then you get out and you have to turn this wheel, and that cranks up the boat and leaves it out of the water. But if you've ever used one, or if you kind of imagine it in action, in order to lift this boat up, you know, a couple feet out of the water, you have to turn this wheel hundreds of times. Okay, now you're moving this wheel a great distance many times, and it's because it's exerting a large force on the axle, you can lift the whole boat out of the water, but you have to turn that wheel hundreds of times to get the boat just out of the water. So it's magnifying your force, but you have to do it over a greater distance. So, you know, I sound like I'm repeating myself over and over because that's what simple machines, that's always the trade-off in these simple machines. We trade off distance for force. We can use a lower force, but we're going to have to do it for a greater distance. All right, so that's the end of our notes for today on these three simple machines. I believe it's going to be Miss Morrow with the next videos on pulleys and levers. So over the next few days, you're going to be doing some activities where you're going to look at examples of these simple machines and calculate mechanical advantage to help you understand them a little better. So hope you guys have a great day. Okay, hope you find some time to get outside, even if it's a little wind and cold. Go out for a walk your dog. And I hope that you have a good day, have a great weekend. I'll see you guys in our Google Meet coming up. Okay, see you later.